Hello, everyone, and welcome to today's hardwear.io webinar. I'm Antriksh, and I will be your host for today's session. I'm glad to welcome Marina, who will present to us on the topic artificial intelligence for fault injection parameters selection. Before we start the presentation, I would like to make some quick announcements. I would like to thank all of you who submitted for our hardware.io USA conference CFP. The selection is going to be tricky, and we will have an amazing set of speakers lined up, announced probably in the next week or so. We have also carefully selected 7 deep technical trainings for you and prepared some very exciting CTFs also for the USA edition. I would like you all to register, and I will copy paste the link in the Zoom chat for you all. Our presenter today, Marina, who is a PhD candidate at TU Delft and also a researcher with ST Microelectronics Lab. Her research mainly includes application of artificial intelligence with a focus on fault detection and side channel attacks. In today's webinar, she will give an overview of state-of-the-art results with AI techniques for fault injection. She will also cover memetic algorithms for laser fault injection and the role of initial population for reaching faulty target behavior. Some housekeeping rules for everybody. The presentation will be for 30 minutes, followed by 10 minutes for Q&A. If you have any questions, please use the Zoom chat window to ask. Since we'll be the moderator, I will read out the questions after the webinar presentation is complete. Also, this webinar will be recorded and uploaded on our YouTube channel for future views. So without any further delay, Marina, I would like you to start your presentation.
Thank you. Thank you for the introduction. I'll just share my screen. Okay, you should be able to see it, right?
Absolutely. Go ahead.
Thank you. So thank you for the introduction. And yes, I'm Marina. I'm a PhD at TU Delft. I'm supervised by Stepan Picek, and I also collaborate with ST and Daniele Fronte from the company. So today I'll show you how we can use artificial intelligence for fault injection parameter selection. So let's start with security evaluation. So hardware devices that we want to keep secure, they need to go through evaluation of their security. And how is this done? We have the security analysts that are here as the attackers, and they are trying to attack the device to gain, I don't know, unauthorized access or extract some secret information. And for this, for attacking the hardware, we can use implementation attacks such as side channel attacks, where we use side channel information like power consumption to gain knowledge about the device, or we can use fault injection attacks, which are the active attacks, where the attacker is making some perturbations about the environment and trying to introduce faulty behavior of the device. So here we focus on fault injection attacks, and it has like 2 phases. So we introduce the faults. We are trying to change the environment of the device to make it behave like have some errors and faults. And then after this, we would analyze the device responses to actually get the secret information on some other game. We have differential fault analysis as the example here, where after introducing the faults, we are analyzing the correct and faulty output pairs and compare them to get the knowledge. But for this presentation, I'll be focusing on improving the part where we are actually introducing the faults. So how we can introduce faults? There are many examples, and we have voltage glitching, clock glitching, electromagnetic fault injection, and laser fault injection as optical fault injections. We can also change the temperature and so on. And all these techniques have a problem of choosing multiple parameters required for the effective faults. So why is this a problem? Because we have a large search space. For example, here from the paper below, where authors use genetic algorithm to improve the electromagnetic fault injection. They calculated, so they used 5 parameters. They had a chip size of 24 by 24 millimeters with an error of the motor stage 0.05 millimeters. And they calculated that if per laser shot per location, they needed 0.16 seconds. The exhaustive search would take 29,000 years. So this is quite a large number, and we don't have this time in security evaluation. Also, if we look at laser fault injection, if we use 5 parameters with very reduced intervals for the possible values, and again, we say that it needs 0.16 seconds per the point. With these reduced intervals, we had 31 and 7 million possibilities, and this would take 59 days. If we didn't reduce the intervals, it would also be years. So we can use some knowledge about the target device that we are attacking to reduce the area we want to test and then do the exhaustive search. We can also use random search, but these techniques are either time consuming or in the case with random search, they are not non-deterministic and we cannot rely on them. And additionally, the measurement results obtained in one setup cannot easily be reproduced by another. So how was this trying to be handled? Is that people try using evolutionary algorithms to select the parameters. And what are evolutionary algorithms? So they are approximation algorithms inspired by biological evolution. And usually they are used for various optimization problems and were quite effective. So what people used for fault injection were genetic and memetic algorithms. And here are some papers where these algorithms were used for voltage glitching and electromagnetic fault injection. And now I'll describe 2 ways we can do this. We want to improve the parameter selection for the laser fault injection attacks. So this is the setup of the laser fault injection attacks. You can see the setup. So this is a motor stage, which you can move in the X and Y coordinates to move the location of the laser. And here is the laser coming through the microscope. And this is just a close-up, so you can see how the device is mounted here. And all these wires are here to actually measure the device responses, so how it behaves. And there are many parameters for laser fault injection attacks. So as I said, we can choose where the laser will be shot. So you can choose the X and Y coordinates on the target device. We can choose the distance from the lens of the microscope, the spot size of the laser, then also some laser settings. So there are different laser types and with the different wavelengths. And we can also, for pulse lasers, choose the pulse width, repetition rate, duration of the pulse, power, and so on. There are many parameters. So this is the first setting I will explain. So you can see below, this is from the paper called a phase characterization method for semi-invasive fault injection attacks. So they propose a methodology to perform phase characterization of fault injection impact on a target depending on the possible attack parameters. And their method is reducing the time needed to identify the optimal attack parameters. It increases the parameter coverage and therefore the quality of the results is improved and the chance of missing the optimal parameters is reduced. So to measure this, they propose 2 metrics. So one is called level of influence, LOI, which is the percentage of non-normal responses from the device. And we have impact score, which gives us the relevance of these FI settings, because we give weights to specific class. So the responses of the device are categorized into these 5 classes. So success, changing, mute, reset, and normal, where success is what we want. So we get exploitable faults, and normal is when when the device behaves normally after introducing the faults. So the method, so we uniformly distribute the X and Y coordinates over the entire scan area. And then we use laser pulse width and laser pulse amplitude, which we test on all of these locations to get the impact on the device. And firstly, they generate the sensitivity curve by finding the golden point and then search the rest of the curve. And after this generation, we will predict the level of influence using deep learning. And now I'll describe this in a bit more details. So finding the golden point, what is a golden point here? So this is the first obtained fault injection setting that reaches the target level of influence. Of course, we have a tolerance here, which would be this point here in the figure. And it's found by diagonal search, where both the laser power and laser pulse width are simultaneously increased by a certain step to find the point. If the level of influence exceeds the maximum, so target low plus the tolerance, and we didn't find the golden point, then we use binary search to trace back to a lower setting with the desired level of influence. So after we found this golden point, we go into the finding the rest of the curve. So from the golden point, we will search to the left and right side individually, and the procedure is the same. So for example, for the left side, from this golden point, we will be decreasing the X here, which is the laser power, by a certain step. And then if the level of influence with this setting will be 2 weeks, so below the level of influence that we desire, then we will use binary search to increase the pulse width. And if again we get the level of influence which is over the desired value for the level of influence, then we will lower the laser pulse width. So then comes the prediction part. They use multi-layer perceptron. They used specifically this structure, which is shown in this figure. So they had 2 inputs, then 4 hidden layers and 1 output. The inputs were the FI settings, so laser power and laser pulse width. And then the output was the level of influence. The challenging thing for this estimation is that because of the sensitivity curve, this will only be our training data set, and it's quite small, so this was quite challenging for the MLP, but it was still proven to work fine, which I'll show later. And just now for the experimental setup they had, so they were attacking the beginning of the last round of DES and AES encryption algorithms. They didn't describe all the details about the target devices because of their confidentiality. And they used the infrared laser. And here in the table, you can see the values they use for the laser pulse width and the amplitude, and their target level of influence, which was 50%. So now for the results, I will only show on the DES. So this is their generated sensitivity curve. So they only have 59 measurement points. And on the right side, you can see the exhaustive search. And you can see that this sensitivity curve really shows us an overview of the target behavior, because we can see the line between the weak settings and then the stronger ones. So yeah, the color is representing the higher level of influence here. Then from the sensitivity curve from the previous slide, they use this information to make a prediction using the MLP. And as you can see, this is their final result from the predictions for the level of influence. And on the right side, you can see the error from the exhaustive search. And it is showing us that it is quite close, and that we can really use these predictions to give us an overview or estimation of how the target will behave. And then we use the level of influence, but actually if we want to choose the optimal FI settings, we will use the impact score. because it gives us an overview of how relevant the FA settings that we tested really are. And here is the sensitivity curve points with the impact score instead of the level of influence. And we can see that the higher the power and lower pulse width are something we would go for. And these are the results for the exhaustive search. Again, the sensitivity curve gives us a really good estimation and overview of the behavior. So some of the additional results they report it is that their results are transferable between the different samples of the same target, and their method can be applied to other semi-invasive attacks as well. So for the future work, they mentioned that they would further investigate the advantages and limitations of the method for various setups and targets, and also explore the usage of neural networks in estimating the impact on non-measured areas. So now I'm switching to other work, which we will show. So parameter selection using evolutionary algorithms. So as I said, this was already done for voltage glitching and electromagnetic fault injection using the genetic algorithms and memetic algorithms. And now I will show you how we can use memetic algorithm for the laser fault injection parameter selection. So what is memetic algorithm? So this is a combination of a simple genetic algorithm with a local search. And here for the local search, we use Hooke-Jeeves algorithm. And here you can see the flow of this memetic algorithm. So since this is based on inspired by biological evolution, usually these algorithms are based on a population of solutions. So we start with initial population, which we then evaluate. We need to know how good or bad our solutions are in the populations. So this is this step. After this, we will check the termination condition, which can be either the number of iterations for the algorithm or a number of evaluations or something else. And after this, if this is met, then we will, of course, end the algorithm. If not, we will go and do the genetic algorithm operators, which are selection, crossover, and mutation. And after this, we will go into the local search. So this GA operators. So first of all, we have selection. So from our set of solutions in the population, we will try to select the best ones, which are based on the fitness, so based on the evaluation. So usually the better the fitness, we will have more chances of these solutions to be selected. And because we believe that the better, if they have a better fitness, then they have better genes inside. And then we mix them together in the crossover. And then after this, we will also do mutation, which gives us a little variations in the genes. And this brings us diversity into the population. And after these operators, we go into the local search. And this is how we acquire a new population, which then again goes into the evaluation. And this is one iteration of the algorithm. So to explain it in more details, so as I said, we have the population of solutions. In our case, the solutions are a set of parameters. So what we use in this work is the location, so X and Y, the delay, laser pulse width, and laser intensity. And this is what it would look like. So it's a population of size n, for example, and then this would be all the parameter sets in the population. And after the evaluation, they get these fitness values, so how good or bad they are. And then I will describe the evaluation functions, so how we evaluate our solutions. So we conduct the laser shot several times for each solution. And since the motorized stage, movements of the motorized stage are really time expensive, what we do is we also include a sorting algorithm. So we sort the solutions in the population based on the X and Y coordinates. And we do this using a greedy algorithm based on Manhattan distance between these points. Then we also categorize the device responses into the fault classes, and we use pass, mute, fail, and changing. So pass is when nothing changes in the execution of the device. mute is when the device doesn't respond, and fail is when we have a faulty output. And changing, since I said that we have several laser shots per one solution, this is categorized when in these multiple shots, we have several of these classes. So the device response was changing. So how do we give the fitness values? So fitness values are given to the pass, mute, and fail by the user, and we use these values. And then for the changing, we calculate as the percentages of how many, this is the fitness of the pass fault class, and this is the number of pass classes that occurred. And then this is summing all of these are the number of measurements we took for the per parameter set. Now the genetic algorithm operators that we used, for the selection we used roulette wheel, and here once we give the fitness value to the solution, the better the fitness, the more chances is that this solution will be selected. Then for the crossover, we use average crossover. So these are the two parents, and then we just took the average for the offspring, for the child. For the mutation, we use uniform mutation, which means that each of the parameters could be randomly altered. So for the local search, as I said, we use Hooke-Jeeves. So which solution we took into the local search? So we consider solutions with a fitness greater than 85% of the maximum fitness, which was 10 in our case for the fail class. And from these solutions that satisfy this condition, we at most took 3 randomly selected, because if we allowed all of them to go into the local search, then we exploited the local search too much. So how Hooke-Jeeves works. So let's say we have 2 dimensions, and this algorithm has two steps, the exploratory move and then the pattern move. So if this is the starting point, we will first explore the first dimension. So here it's left or right. And where we see the improvement, we move in that direction. So we keep this. And then we look into the other dimensions. So D2. So this is up or down. We see that we have an improvement here. And then we see that we moved from this point to this point, which we then use for the pattern move. And we just double this and move into our X2, our next point. Then again, we will repeat the exploration move. So the first dimension, if we see improvement, then the second dimension, we see no improvement, and then we go here because our optimum is there. So for this experimental setup, for this work, we tested on a chip from ST, and we shot the lasers while loading the data from the register. And the fault was if this data was not correct. And again, for the confidentiality reasons, we cannot share many details about the target and also the intervals for the parameters. But we can say that we did use a subset of the available values where we use previous knowledge about the target, and we used number of measurements per solution is the number of laser shots for one solution, which was 5 in our case, and then each of the settings we tested 5 times. So we were comparing random search with our memetic algorithm. So for the random search, we didn't allow duplicate solutions, so duplicate parameter sets. And for the memetic algorithm, we used the random initialization for the initial population. And then we had 200 iterations, a population size of 36. Elite size, I didn't mention this. These are just the number of solutions from the population that will go into the next generation without any changes. Because usually these are just the best ones. So the best solutions from the population are just taken into the next one. And the mutation probability, we keep it low, because if it's too big, then the search goes more into the direction of the random search. So here in the table, you can see the results. We run each setting 5 times, as I said. This was run 5 times, and memetic as well. So here, these are the average results of these 5 runs. So on average, you can see that for random, we got only 0.9 fails out of all of the tested parameters. And for the memetic, we had 31. So this is a big difference. So we conclude that compared to random search, we would really prefer using a memetic algorithm. Also, just to explain this variation, so on the average is because of the local search, because sometimes there are solutions that are going to the local search, and sometimes there are not. And next, we look at the initialization methods for the population. As I said before, we used first to compare with the random, we used the random initialization, which is very common. And then we looked at other techniques which would give us the, well-distributed samples. So we have Latin hypercube sampling. And here on the figure, you can see this is an example of how random selected points would be look like. So we have a lot of area that is not covered. And with the Latin hypercube sampling, each point has to be only in one row and one column. So there should be no overlap. And this is why we have better distribution here for the samples. We have another version of this Latin hypercube sampling, so with multidimensional uniformity. And this helps us in problems that have more dimensions, so more than 2. And in our case, we have 5. So this is why we use this. And we also explore the Taguchi method, which is based on orthogonal arrays. Specific for these arrays is that, so you can see that this is an example of an array with strand 2. So this strand 2 is, you take 2 columns, and each of these tuples will repeat once and should cover all the possibilities. So as you can see, we have a combination of 1, 1, 2, 2, 1, 2, 2, 1. And if you look at any of the columns, 2 columns, you will again see every combination repeating the same number of times. Here it's only 1. Here this array has 4 experiments. So this will be the population size in our case. And then this has 3 columns, which is 3 factors. In our case, this will be the number of parameters, which is 5. And then for each of the factors, we give it a factor level. And here it was 2 factor levels. And later I will describe how much we used. So here we have the comparison of these methods with a smaller population. So we had a population of 36, elite size of 2, mutation probability 0.05, and number of iterations 200. So for the Taguchi method, the array had 36 samples. As I said, this has to be the population size. The strength was 2, and factor levels were 3, 3, 3, 2, 2. We gave the x, y, so the location and the delay, more factor levels, and 2 were for the intensity and the pulse width, because the intervals were smaller here. And you can see in the table that the Latin hypercube sampling with multidimensional uniformity was the best. But what you can also see is that the number of tested parameters here was also the highest. And on average, so there's a difference between the worst and the best initialization here. It's only 5%. So basically, on average, we don't see any significant difference in these performances. And if you look at the bigger population, so here the population size was 128. We also increased the elite size then. The probability for the mutation and number of iterations is the same. For the Taguchi method, as I said, we use 128 samples. strength 2 and factor level 2 for all the variables. And here we have the Taguchi as the best one. Again, there is no significant difference on average, but the difference between the worst ones, so Latin hypercube sampling and the Taguchi method, was decreased. And then what we also looked at was the stability of the performance with the different initialization methods. So here, this is the stability where we had a smaller population of 36. So you can see that the number of total parameters tested is varying, as I said, is the case for the memetic algorithm. And you can see that for the number of percentage of the fail classes, the most stable one was the best one also. So Latin hypercube sampling with the multidimensional uniformity. But we can see that the best results here were not the best when considering all the runs. So in the random and Taguchi, we had better results. But also you can see that Taguchi had, when it had the greatest number of total parameter sets, this could be the case when it got the number of fail classes. So then we can also look at the stability with the bigger population. Again, I show here the total parameters that are tested and the percentage of fail classes. So we can see here the Taguchi was the best, and it's also a lot more stable than with a smaller population. And the random is also more stable here. But the stability of the Latin hypercube sampling with multidimensional uniformity was, the stability was a bit decreased. So a little bit reasoning behind this. So as I said, it was more stable with the smaller population. So how this works is it divides the number of samples, it divides the values of the parameters, the intervals, into the number of samples that we use, which is in our case the population size. So when we had 36, we had less intervals. And if we had, for the same parameter interval, if we had more samples, so 128, a lot of the values get mapped to the same value. And this could be the reason why this happens, why the performance was a bit decreased. And for the random, the stability improved with a larger population because we do not allow duplicate parameter sets to be used. So it gave a better distribution initially. And the Latin hypercube sampling, the first version, was not really good in any of the cases, and the problem could be this dimensionality of our problem, where we have 5 dimensions, actually 5 parameters. And so to conclude, we show that with memetic algorithm, we improve the results compared to the random search. So from 0.9% of fail classes we found in the random search. With the random search, we had 31% with the memetic one. As I already said, on average, the performance with different initialization techniques didn't have that much influence, considering the number of fail classes that we find. But still, if we consider the stability, we can see that methods like Latin hypercube sampling or Taguchi are maybe preferred because they give us well-distributed samples. So our conclusion is that, or better, our recommendation would be that if we don't have great overhead, it is better to use sampling that promotes well-distributed samples for the initial population. And this is more the case even when we have a smaller population. Also, just to mention, we did not observe that the genetic algorithm was causing any issues because of the exploratory characters, such as that it would break the target. So for future work here, we would need more experiments and test on different population sizes. And also, we would like to try orthogonal arrays with more factor levels, as this could improve the Taguchi method even more. And also what we would do is explore the usage of neural networks for predicting responses for not measured parameter sets. So I hope this shows how we can use artificial intelligence for fault injection attacks. And thank you for your attention. And if you have any questions, I'm here to answer.
Thank you, Marina. We have few questions. I will read them out for you. In the meantime, if anybody else has questions from the attendees, please send them across via the Zoom chat. Okay, the first question is, how was the attack synchronized to guarantee that the fault happens exactly during the copy of the value?
So we used the delay of the laser. And as I said, we used previous knowledge. So I worked on this with Daniele, and he already made this possible. He mounted everything.
Okay. I will read the next question for you. How do you select the golden point?
Okay. You mean the target level of influence? Or so they used in the paper, they used 50%, as it would divide us into weak or stronger FI settings. But the golden point is, let me maybe again share the slide. So they use diagonal search. Just a second. So they use diagonal search. Yes, where they were simultaneously increasing both the laser power and the laser pulse width. So these are kind of representing the tested points before reaching the golden point. And then they use the target level of influence, the desired value they wanted, with, of course, the tolerance, because it would be too hard to reach the exact value. And then once we get the FI settings in this interval, it was accepted as the golden point. I'm not sure if this is answers.
Okay. Marina, I would just like to invite Daniela, because he's also on the webinar, to add more points to the previous question.
Okay.
Yeah. Thank you. Actually, I would just add some info for the attack synchronization. We used to monitor the I/O communication bus, and there was a trigger event when the trigger event was recognized. The fault was injected. That's just a compliment.
Okay, great. Thank you.
Thank you.
I'm reading the next set of questions. Either you or Marina could answer them. What would you change in your method for larger data size models?
I'm not sure what this refers to.
Mohawk, if you could elaborate your question in the Zoom chat, then I can come back to that question. Let me move to the next question. How do you characterize stability in selecting initialization parameters?
Okay, so as I said, we have 5 runs. So the stability is actually the variance in the results. I'm just going to the slide. Okay, maybe this would be easier. Okay. So this would be kind of the variance. So this is the X here is the average. And then we can see the 5 runs. 5 is maybe for statistical also too little. So as I said, we should increase the number of experiments. But we can see the variation. So the maximum fail classes found by the Latin hypercube sampling here was 34%, and then the lowest in one of the runs was 21%. So this is what we looked at when we were considering the stability.
Okay, there's one more question. have you experimented with different genetic operators, selection, crossovers, and so on?
So for now, no, we have different implementations, but here we didn't change it because we were also looking only at the initialization method, and so we kept everything fixed. But different operators, there are many, so yes, there could be others applied.
Okay. Is there any other question from the participants? Okay. If there are, you all can always send them on the YouTube channel when we upload this recording of the webinar, and we will pass it on to the presenters to get back to you all. Thank you, Marina and Daniel, for this research and sharing it with us at hardwear.io. We hope to have you all again in the future, and I can see you wearing the mask, so stay safe then.
Thank you.
Thank you, everybody. Bye-bye.
Bye.